busy day.
Yeah, for sure, for sure. All right, guys, I've got 4 o'clock. Maybe we can go ahead and get started. It's good, great to see all of you. I hope that you had a nice weekend and the extra hour of sleep. It seemed to just put my other students even more to sleep. I don't know. Is it just something about like the more sleep you get, the even more tired you are? That's happened to me before, like where I slept till noon one day and then I was like even more tired after that. Like, why did I do that to myself? So anyway, some people I think got too much sleep. I don't think that's necessarily the case for me. I kind of got myself, I don't know, not feeling the greatest. So I'm gonna muddle through as best I can here. I've got my syrupy drinks and all that to try to make it through the lesson here. But if you have questions for me afterwards, it'd be really nice if you would swing by my office hours on the earlier side that you can make it. I know some of you have class right after this, and maybe if you want to talk to me, you have to do it later in the evening. But by 10 o'clock, I have a feeling I'm going to be pretty much a zombie, which is when my office hours normally end. So just to try to catch me on the earlier side if you're able to do that. Let's see, we have made it into November, and we have only really 3 weeks of class in November as compared to the 5 that we had in October. And within those 3 weeks, we actually have a day off. So next Tuesday, we don't actually have class. I haven't decided yet whether I'm going to have a video for you guys to watch during that time. We will definitely not have class. They don't even open the campus. I mean, you can come, but the building won't even be unlocked. And I mean, you have to be a diehard to show up next Tuesday. But anyway, I won't be having a formal lecture, but I may have some video for you to watch if I feel like it would be helpful. I did send you guys a couple of emails this weekend about kind of what's coming up in the next couple of weeks. So I just wanted to let you or remind you, I guess, that we're going to have a quiz on next week on Thursday. So this is Thursday, November 13th. And there will also be a homework assignment as well. So just be ready for both of those things, kind of on top of each other a little bit. If I need to, I'll always extend the homework a little bit, but I don't want to extend it too much because we have an exam the following Thursday. So our second midterm is on Thursday, November 20th. So yeah, we have a normal week this week. There's a homework assignment and then I hope that you've already started working on. It's only got like 5 problems on it, but a couple of them are going to take a little bit of time, I think. So there's that homework that's due this Thursday, and then there is next week a quiz and the homework for next week as well. So just in case you didn't get a chance to look at this, in Canvas, I'm kind of highlighting it here on the screen over there. There's a folder called Midterm 2 Resources. If I go in there, I've updated all of this stuff. You can see I've got sample. So just like the last time, I've got 2 sample midterms in here. So there's a lowercase one and an uppercase one. These are actually the 2 midterms I gave the last 2 times I taught the class. So you've got a couple of practice exams there. There's also a document that is just like an overview of all of the material. That's called Midterm 2 Review, which also has some extra practice problems in it. And I've solved those problems in this other document. So if you want to try those other practice problems, then you can check your answers that way as well. I'm bringing this up now because maybe some of you, while you're studying for the quiz, would like to kind of get a jump at looking at some of this stuff, because it will be kind of all obviously related to what the quiz will be on. And then I've got this review session along with the solutions to the review session. So somewhere along the line here, if I open up this Midterm 2 review file, I don't know how well you guys can see it from where you're at out there, but if I pull this down, that's probably not too readable, but right here where my cursor is, I am going to do a couple of review sessions. I was real happy with the turnout for the first midterm. We had a lot of people coming to the review. These will be optional. And they will be recorded. So if you cannot make it, but you don't want to miss out on anything, you might just be aware that I will send out a link with these on it. But if you are able to come, it's probably better to come. So this will not be in time for the quiz, obviously. The quiz, by the way, it's just the same as a homework assignment. It's not like a big deal that much, really. It's just to kind of get you to study a little bit. But the review sessions then are on the Sunday and the Wednesday of the week of our midterm. And again, I'll record both of these and send them out. I'll also have some extra office hours. I haven't quite decided exactly when I'm gonna throw those in there, probably on Wednesday, which is a day I don't normally have office hours. I'll probably have office hours on that Wednesday, the 19th, before the review session or something like that. So that's kind of my plan. This document, this would not be a bad, I probably would not recommend just launching into the sample exams, right, without doing any preparation first, because all you're gonna do is kind of scare yourself. Like, oh, I'm not really ready for this, and these problems look really hard. It would be better, I think, to maybe kind of go through this, just read through it, see if there's any things you want to kind of just brush up on first. And then, once you feel like you've done at least a reasonable amount of studying, it could even be after the first review session if you wanted to. You could then try one of those sample exams. And if that's good enough and you're feeling good at that point, you could just leave it at that. But then if there are some issues that come up, the way I like to do it is, see, I didn't used to put two sample tests. I used to only do one. And so the students would only get one crack at it. But this way, and this is only optional if you have time for it, but you could try one of them and then learn from that and then try the other one. So I would, in an ideal world where you guys have nothing else going on, you might actually be able to do all of that. But I understand that you guys are busy people and I don't expect everybody to do all this stuff. This is really just optional stuff, including the review sessions and all of these documents. You can also, if you don't want to do the review session, you can just read I've got all the review session questions and the solutions just typed out. So you could just, like, if you want a faster rush through on all that stuff, you could just do that too. So anyway, so this is already up there, and that way, if you are trying to figure out what you're going to do to study for the quiz next week on Thursday, this would be something you could dive into. We will not have covered everything for the quiz. I think I said the quiz was going to cover chapter 7. We did not do 7.3 though. So it was 7.1, 2, 4, and 5. And also chapter 11 through 11.4, which actually we're going to be doing today. So that's for the quiz. But then you'll see if you really look at the sample test, you're going to see some problems in there that are based on stuff from chapter 12, which we haven't gotten to yet. So just ignore that stuff if you see it until we actually cover it. Okay, so I hope this will be helpful, but I also don't want it to be overwhelming. So just ignore whatever you don't have time for. Make the most of whatever you can do, and then just let the rest go. Okay. Does anybody have any questions about that? What's coming up? That's gonna keep us busy for most of November. After this midterm, we're off for the last week of November, completely off. And we come back, we have just 2 weeks left at the beginning of December. So there won't be that much more material to cover a couple weeks or so. That should be pretty good. Okay, well, anyway, if you think of any other questions, just let me know. Yeah, so on the board here, I have tried to recap where we left off on Thursday last week, and that was a while ago. It was 1 hour longer ago than normal as we set our clocks back. So we've had even more time to forget everything than even in most weeks. So let's just get it back in our mind again here. We were starting to talk about this very complicated subject of a Hamilton path or cycle. So these are paths or cycles in a graph that visit every vertex exactly once. Okay. And I think I mentioned last week that this is actually sort of an ongoing topic of research, because it's been very difficult to develop any characterizations of the existence of these things. So, typical problem is I'm going to give you a graph and I'm going to ask you, is there a Hamilton, let's say, cycle in that graph? So if there is one, you can prove that by just exhibiting it, just saying, I'm going to start here and then go here and then go here and then go here, and you just write it out. But if there is not a Hamilton cycle, we have to disprove it rigorously. And I've made some notes here. that we've kind of looked at these already, but just to reiterate it, and we're gonna practice this today a little bit. These are some notes that might help us in analyzing whether there could be a Hamilton cycle or path in a graph. In particular, every vertex is being visited exactly once. So assuming it's a cycle, you would have to use one edge to arrive at that vertex and then a different edge to leave that vertex. And so that's two edges, exactly two edges incident with each vertex are going to be used by this cycle. And then all of the other edges basically can be ignored. They can be thrown away, they can be removed. We cannot use them again because using more than two edges would involve visiting the vertex more than one time. Right? So that's what that first bullet point says, right? And the other comment that we made, and this is often how the contradictions come up, specifically for Hamilton cycles, is that if you had some hypothetical Hamilton cycle, sort of a by way of contradiction approach, right? Suppose there is a Hamilton cycle, then you start looking at your graph and you start saying, oh, well, then I must use this edge or I can't use that edge or whatever. You sort of use this first bullet point as best as you can. And you might force yourself into what I call a premature subcycle. This would be a cycle that has not yet visited every vertex. So you have not got a Hamilton cycle, but you do have a cycle that you can't really build off of because again, if you tried to build more edges off of that subcycle, you would have 3 or more edges incident with a vertex being used, and that's not allowed, right? So it's that idea again. So these two bullet points are really good drivers of the arguments that we can make about these types of graphs. But again, there's no smoking gun here. There's no like just clear-cut thing we can look at. You'll remember last week, right? We talked about the open and closed Eulerian trails, and that was a very different scenario where, as long as the graph is connected, it'll have an Eulerian trail if and only if, and we had characterizations involving the degrees of the vertices. It was super easy, right? You could just look at the graph and in a matter of a few seconds, you probably know whether there exists an Eulerian trail or not. Not the same thing for these Hamilton paths. So it's kind of interesting. Okay. But there are a few results. I of course am not going to be able to do decades and decades of research papers on Hamilton paths and cycles. So I'm just going to pick a couple of things that the book has focused on as some sort of one-way theorems that we could have. And I mentioned one of them last time. So I'm going to recall it for you here, and then we'll state this result. So we can try to at least get some results going. And this first result is based on something called the Ore property. So O-R-E. This Ore property, and what this says is for all pairs of distinct vertices, X and Y, that are not adjacent. So what does the Ore property say? For all pairs of distinct vertices X and Y that are not adjacent, the degree of X plus the degree of Y should be at least the order of G. Remember, the order of G is just the size of the vertex set, the number of vertices. So what this is just saying is that the Ore property is basically just saying that there's lots of edges that are somewhat spread apart in the graph because X and Y are not adjacent. And the number of sort of edges coming into X and Y, which is the degrees of these vertices, adds up to a fairly sizable lower bound. If this Ore property is true, then your graph has a Hamilton cycle. So that's the theorem. I wrote it down, but I was kind of rushed at the end last time. So theorem 11.3.2 in the book just says if my graph G has this ORE property. Right, so if the graph does have that property, then G has a Hamilton cycle. So there's one of the few results that's easy to state in a sort of a positive direction. So we can say that as long as G does have this ORE property, which kind of just says you have lots of edges spread out throughout the graph, well, then you will have a Hamilton cycle. As like a special case of this, we could write down a corollary at the same time that kind of goes with it. 11.3.3. And this one is just a special case of the theorem I just wrote down, which is that if every vertex in G has degree at least half of the order of G. So if every vertex has the degree at least half of the total order, then G has a Hamilton cycle. Then G has a Hamilton cycle. So this just means that if, there's lots of edges in the graph. That's basically what that's saying. There's lots of edges and they're fairly uniformly distributed, okay? I mean, you can have a graph that has a ton of edges, but then there might be one vertex in that graph that is only having degree 2 or something. Well, so there could be one vertex that only has degree 2. That one vertex could screw everything up, even though you have all these other edges in the graph. It might not be possible to draw a Hamilton cycle if you even have 1 or 2 vertices that are of low degree. So we're putting a lower bound here on all of the vertices, and we're requiring them all to have a fairly large degree. Let's just write down maybe an example. Oh, by the way, is it clear that this corollary falls from the theorem here? If every vertex has degree that's at least half of the order of G, then when you add 2 of them up, it's at least the order of G, right?
Yeah.
So yeah, the proof to say of this is clear from theorem 11.3.2. It doesn't really need much more clarification than that. But let me write down an example here, so we can kind of just look at it. Let's suppose I have a graph that consists of a square. So I'll go ahead and draw out the square like that. And then I'm going to put a vertex in the center of this square. And on Thursday last week, I drew these diagonals across the center of that square. We had this graph up on the board. I don't know if you remember it. This one did not have a Hamilton cycle, but if I add one more edge like that, then I want to take a look at this graph and see whether it would have a Hamilton cycle or not. So of course, one thing you can do, of course, is to just try to draw the Hamilton cycle. And it may not be that hard. With a graph this small, it's probably going to be pretty easy to just draw it. But in general, for a large or complicated graph, just kind of winging it by just trying to play around with it might be a long process that you don't even know if it's going to succeed. So I prefer usually, if I have a theorem, I can check first. I'd rather do that. Let's write down the degrees of these vertices, just so we have them. 3 and 3 and 3 and 3 and 2. Now, half of the order of this graph, so the order of this graph is what? 5. So half of that is 2.5. Does every vertex have degree at least 2.5?
No.
No, we have one vertex that fails, so I cannot apply this corollary. But let's go back, because this is a weaker assumption over here about this ORE property. So would it be true that the trouble with the ORE property is you have to look at all pairs of distinct vertices that are not adjacent. That could be a lot of, pairs to consider. So like if I start up in the upper left corner and call that X, then obviously I don't have to look at any vertex that's adjacent to X. I have to look at this one though. Well, if I add 3 and 2, I get at least 5, right? The question is, would there be any way to take two vertices that are distinct and which are not adjacent and get a result that is not at least 5? And you can't, because you only have one vertex of degree 2. So if you use two vertices here, your degrees are either gonna add up to 5 or 6. So the Ore property holds. So this is kind of my solution here to this little example. The Ore property holds. So G has a Hamilton cycle. And I am sure that you guys could write one down. Remember, any vertex of degree 2 will be required that you use the edges that are incident with it, because you have to use exactly 2 edges that are incident with each vertex. So these 2 edges would have to be used, right? But you can see that you could easily like go here and then here and then here like that, and that fills out a nice Hamilton cycle. Okay, so obviously there's no substitute for just writing down the Hamilton cycle. So far, so good. As nice as this theorem is, it is actually not true in the converse. So that's the problem with this theory, is we don't have any nice characterizations. Let me give you another example to show you that. Suppose we just take this example. Okay, I'm really making these examples easy. I'm just gonna take a pentagon. That's my graph. That's my graph. Well, that graph obviously has a Hamilton cycle, which is just the entire cycle of the graph itself, right? So this has a Hamilton cycle. However, it fails this Ore property, because the degree of every vertex is 2. So if you add up the degrees of any 2 non-adjacent vertices, it's only going to add up to 4, and that's not greater than or equal to the order of this graph. So, but does not have the Ore property. So this is just the converse of our theorem, and the converse actually does not hold. So the converse doesn't hold here, which is kind of unfortunate. Okay. Questions so far? Yeah, Mason.
For your first little like square graph,
Yeah,
so all the vertices have half order except for that 2.
yeah,
Would it be fair to say that we only need to check the Ore property for that 1?
absolutely. Yeah, we could just focus on this vertex and just check it compared to the others. Yeah. When there's only one vertex that is kind of below the average, then you could just pick that one with any others and just make sure that the sum of the degrees is at least the order of the graph. Yeah. Yeah. So these are pretty easy examples here. Let's try a slightly bigger graph. Questions so far? Yeah, go ahead.
So for the Ore property, I think that vertex is like the bottom left.
This one?
No, on the.
This one?
Okay, so then the vertices that would not be adjacent to it would be the other 2.
This one and this one.
Right, but if I add up those degrees, that adds up to 6, right?
No, you're not adding, you're only adding 2 vertices at a time.
Oh.
So you're adding like this one with this one would be 4, or this one with this one would be 4.
Oh, I see.
Yeah, it's just 2 at a time. Any other questions so far? Is it clear enough? Let me give you a slightly more complicated graph, and let's lay out 7 vertices here. So I'll make 2 rows of 3. And then I'm gonna put one more vertex kind of down at the bottom. And on this top right corner, I'm gonna fill out a full square. And then on the left side of this, I'm gonna make it into a bow tie. So I'm gonna draw like an X essentially like that. And then I'm gonna just draw a V down to this bottom vertex from these two that are directly above it. And then I need one more edge going kind of across here. So something like that. Now, in this case, let's actually label the vertices so we can talk about it a little bit better. A, B, C, D, E, F, and G, like so. And the question is there a Hamilton cycle? In this graph. So we'll phrase it as a question, and so part of the battle here is just figuring out what the right answer should be. And I often do not know the answer when I'm just starting to first analyze it. What I would recommend that you do is take advantage of, well, you can try to check this Ore property, but more than likely, it's not going to work, which means you can't really use the theorem. I have vertices here that are a pretty low degree. Whenever you see vertices of degree 2, which is a low degree, those edges would have to be used by your Hamilton cycle. So if I want to visit vertex A, I must use AD and AE. And similarly with vertex C, CB and CF. So without knowing the answer yet, let's just write down what we can say and see if in the process of working on this, we can kind of figure it out, okay? So such a Hamilton cycle must use edges. So we'll write them down, AD and AE and BC and CF. And are there any others? AE, AD, BC, CF. Are there any others that have to be used? The ones that go to G, right? The ones that are incident with G, right? Because G has degree 2 as well. So let's add that to our list. DG and EG. So before I even really take a breath, I can just write all of that down. I have to have all of these edges. And I really would recommend that you get some colored markers or highlighters or whatever you want to help you with this, to visualize it. Because it's just, there's nothing that it's better to look at the graph than to try to read all this, right? So based on what I have there, what would you guys tell me? Mason? There's no Hamilton cycle, and that's because of our second bullet point over here. There is a premature subcycle that is forced upon us. We have to create these 4 edges here. So let's write that down. Creating a premature subcycle that goes from A to D to G to E back to A, like that. So the answer is no, there cannot be. I would be forced to use all of these blue edges, but then I can't add any other edges. In fact, if you want, you can even erase them. So once you've used the 2 edges in blue that are incident with E, you can actually erase, if you want to, these other edges. I wouldn't necessarily recommend that you do this right now in your notes, but you can kind of see what's going to happen, right? I'm also going to, I'm basically also going to erase the other 2 edges that are incident with E, which would erase those 2 edges. And now you see you have disconnected the graph. There's no way to connect all of these vertices into a single cycle. So that's kind of what goes wrong. Okay. There is one other concept here that I have not mentioned yet that we could also bring into the conversation, and it's a pretty well-known concept, so I think I'm gonna define it now. And that's the idea of a bridge in a graph. So a bridge in a graph is just an edge whose removal disconnects the graph. So it's like a critical edge that keeps the graph together. And that turns out to have a little bit of bearing on this as well. So let's get that definition written down. And then we'll see what kind of result we can get from it. Okay, so if there is an edge, so this is the definition. If there is an edge in a connected graph G, whose removal, kind of a weird way to say it, but if there is an edge whose removal leaves a disconnected graph. So remember, connectedness is defined just in terms of whether you can walk from any vertex to any other vertex. So if you've removed this edge and now suddenly you can't walk, maybe you can still walk from some of the edges to others, but you can't walk between all pairs of edges. So if they're all pairs of vertices. So what's happened is you will have left a disconnected graph. The edge that we were just referring to is called a bridge. So a bridge is just an edge that sort of disconnects the graph when you remove it. So, you know, an easy little example of this would be if you had like, I don't know, a triangle here, and then off of the end of that triangle, you come over here and you have, I don't know, some kind of a square like this. I think there's a homework problem asking you to draw a graph that has exactly 3 bridges in it, something like that. And I'm going to suggest for that problem that you sort of make a central vertex that goes out in 3 directions. And then put something up here, put something up here, put something up here, to kind of make a very symmetrical picture. But anyway, that's just a hint for one of the homework problems. Anyway, you can see right here that this edge right here, if I remove this edge, it disconnects the graph that we have. So this is a bridge. That is definitely going to be a bridge. And you can see that if you have a bridge, you would never have a Hamilton cycle because you can't walk across the bridge more than once. If you've walked across this bridge, so let's say you started here, you've got to go visit everything and then come back to here again. So you're going to have to go across that bridge. Why do I know that I have to do that? Well, if there was some way to avoid that bridge, then it wouldn't be a bridge. You could remove it and you'd still be connected. So if you have a bridge in your graph, you cannot have a Hamilton cycle. So that's kind of the theorem here. Let me just state it for the record. 11.3.1. And this just says a connected graph with a Hamilton cycle cannot have a bridge. Okay, so if there is a bridge in your graph, then you won't have a Hamilton cycle, and you can use that as a nice theorem as well. But again, it's a one-way theorem. Okay, it's a one-way theorem. It is absolutely a clear result because again, you can't cross that. See, guys, if you cross the bridge more than once to get from one side to the other and then back again, then you're also visiting those vertices more than once, the vertices that are part of that bridge. So that's against the rules of a Hamilton path. So that's really the reason for that. Okay. But oftentimes, oftentimes, guys, none of these sort of half-hearted results, which we've been writing down, they're all kind of nice and it gives you the flavor of everything, but a lot of times they just don't, none of them really work. And you just have to brute force these things. So I would like to show you one more example here, and then I'll probably turn you guys loose on a little bit of group work to practice it for yourself, okay? But let's try one more example together, which is to show that G doesn't have a Hamilton cycle. Now, give yourself a fair bit of room on your paper to draw this graph, because this is going to be a pretty big one. I've got to make it fairly big to make it challenging enough. So I'll give you guys plenty of time to draw the picture. I hope I will anyway. I'm going to start with a giant diamond. 4 points way far apart on the outside, and I'm going to connect them up just like so. So I'm just going to make this giant diamond here like that. Okay, and then I'm going to come in from the sides and add a fairly short edge and draw these two vertices. It's going to be a fairly symmetrical looking graph. So something like that. And then I'm going to do the same thing from the top and the bottom, except there's going to be two of them on both the top and the bottom. So I've got two of them kind of coming in from the edges on the top and on the bottom like that. And then I have one more vertex in the center. Okay, and that vertex in the center is going to be joined up to the 4 vertices that were brought down from the top and from the bottom. So fill it out like that. And then the 2 that I inserted on the sides are going to be connected up and down to the closest neighbors towards the center of the graph. So I believe I've drawn my picture correctly here. It's just going to be complicated enough that we have to work at this a little bit. I'm going to label these vertices now. So we want to have them labeled. So I'll start over here on the left with A. And then I'll go to B right on the right side of that, and then heading up to C. And D is all the way up at the top. And then E is going to be the vertex in the center. F is the vertex way at the bottom. All right. And then G and H are right here on the side, on the right side, G and H. And then off on the far right, we have I and J. And then somehow I skipped K, so I'll come back and put K right there. It's not a very logical labeling of the vertices, but it's okay. It doesn't really matter. So that's my graph. And I would like to show that there's no Hamilton cycle. So this graph does not have any bridges. It also doesn't have any vertices of degree 2. There is no edge in this graph that you must use. Like over here, we had all these edges that we highlighted in blue immediately. Here, we cannot do that. But we do know that this is a very symmetrical figure. We cannot have any premature subcycles. So I think you guys would all agree that I cannot use all 4 of the big long outer edges. The diamond on the big outside. I could not have all 4 of those, or it would be a premature subcycle, right? So the way I'm going to argue this is, well, first of all, I'm just going to say by way of contradiction, suppose G has a Hamilton cycle. I like to just argue it with that sort of approach. Suppose that there is a Hamilton cycle, and then I'm just going to say by symmetry. So this is a tool that you can use. I haven't really talked about it, but if this graph has a lot of symmetry to it, then without loss of generality, assume, let me just make sure I'm consistent with the one I put in my notes here. Assume that the edge AD is not used by the cycle. So we're talking about the symmetry of the big square, the big diamond on the outside. All four of those edges cannot be used. So let's just kind of imagine deleting that. So just kind of take it off. That is going to force us to use certain other edges. So in particular, if I've removed the edge AD, can somebody tell me what are some edges that we would have to use? AF and what was the other one? AB, right? These two, because there's only two more edges incident with A other than the one we already removed. So then what we can do is we can say, then we must use the edges AB, which I highlighted in blue, and AF. Okay. Now, actually, this gets to be kind of a long-winded paragraph if you kind of keep going like this. So in a minute, what I'm gonna start doing is changing this into a 2-column format. And I'm gonna, in one column, I'm gonna write down all of the edges that must be used by the cycle. And in the other column, I'm gonna write down all of the edges that cannot be used by the cycle. So that's gonna be, in a second, I'm gonna do that just to make it a little more organized. But I don't see anything else so far. That is there anything else that we can say for sure?
No.
It's not really that clear, is it? Not really that clear. So another tool that you can use in addition to symmetry, which is kind of what I used there in the first step. Another thing that you guys can use here is you can use cases. And you can say, all right, I can't force anything else to be true here, but I could make some cases. And I'm looking at vertex B. I'm gonna have to either use BC or BK. Right? So let's do some cases. And case one will be the case when the edge BK is used. Just make sure that when you're doing cases that you actually cover every scenario with those cases. So I'm gonna go ahead now. We have to remember where this graph was at because when we come back to do case two, we'll have to reconstruct it to this point. Okay, but for the time being, I'll go ahead and highlight in blue BK. And I am just gonna make a table now. In this case only, I'm gonna make a little table. And I'm just gonna say, cannot be used in one column. And then in the other column, must be used. So I'm gonna list these edges out in kind of a table format. And I don't mind if you guys write your proofs up for this in this manner. So as soon as BK is used, what else could you tell me about my graph?
Can't use KF.
I cannot use KF or I would have a premature cycle, okay? So I'm gonna remove KF and I'm gonna put it in my list over here, cannot be used KF. Right, exactly. All right, anybody else wanna tell me what I either can or can't, whether I either must or cannot use? KE. Yeah, because vertex K, I only have these two edges now, so KE must be used. Let's fill that one in. I'll add that onto my list over here. KE must be used. Looks good to me. Okay, anything else we can do? I think we can do a bit more.
Not use CB. Yeah, CB.
CB can't be used because I've already hit vertex B with two edges, so I'm not going to use BC. Let's just remove that. Cannot be used, BC. Okay, somebody I haven't heard from, want to tell me something else that I either cannot use or that I must use? Sam, do you have any ideas for me? No? Okay. Jean, do you have any ideas for me?
Say C.
Vertex C?
Yes.
Yeah, if you look at vertex C, you see there's only two edges left. In order to have a Hamilton cycle visiting that vertex, you would have to use both of those edges. Let's go ahead and highlight those. So we must use CD. Oh, sorry, this should be in the must use. CD and CE. Okay, so those are both in blue. I don't know if you guys can see the blue very well. Is it showing up at all? Okay. Actually, I did this example on YouTube using the studio downstairs that has, it's really cool. I'll have to send you the link to it because it reverses the image. And so I look like I'm facing people working on it and it's in all these beautiful colors. So I'll have to share that with you for your viewing pleasure, give you some ideas for teaching this stuff. What else can you tell me at this point? Somebody who I have not heard from want to help me out, Sergio?
So I guess we can't use CG and EH.
Okay, vertex E is done. Let's remove EG and EH. EG and EH. As soon as you've used two of the edges, right? As soon as you've used two of the edges that are incident with a vertex, it's done. Okay, awesome. Anything else we can say at this point with any kind of confidence? Was I?
Wait, we have to use, into D,
Did you say D?
no, sorry, G.
G, yes, the ones that are connected to G, there's only two edges here, I gotta use both of them. So DG and GI, I like it. Yes, let's add that to our must be used list. DG and GI. All right, excellent. Anybody want to help me out any further? Kevin? What's that? Okay, I can remove DJ because we've already hit vertex D with two edges, so I cannot use DJ. Guys, I think we can just about get our contradiction though. Wait, let's go really, what's the fast way to the contradiction at this point? Mason?
You have to use the two coming off H, so.
H, yeah, that's the secret. HF right here, right? Along with HI right here, those must be used. So HF and HI, absolutely true. You must use those edges. And now, if we've done that correctly, you can see a premature cycle. So let's write out what it would be good to actually write the cycle down. I'm going to highly recommend that we do that. So we get premature subcycle. And the premature subcycle, we can just list it in any order. I'll start with A. It goes to B, and then to K, and then to E, and then to C, and then up to D at the top, and then over to G, and then I, and then H, and then down to F, and back to A. And the key thing is that not all of the vertices are listed in that cycle. So you can see there that we've missed some of the vertices like J. J is not mentioned anywhere. Actually, J is the only one that we missed. Came darn close. That was darn close to having a Hamilton cycle, but we are missing vertex J if we do that. So that is only one case. That is the case when you use the edge BK. So now, if you don't mind, I'm gonna redraw the picture. Maybe I'll redraw it over here. And go back to look at how case 2 is going to be. So here's the graph. I'll just draw it one more time for us here. This edge coming in, this edge, these two coming down here, these two coming up here, and then there's the center vertex that connects to those four. I'm just redrawing our picture here again. And this time, I'll go ahead and label the vertices one more time as well. And we'll go back to the spot where we left off. F is down here. G, I, J, H, and K. So here's, I very quickly redrew the whole graph. And we're going to remove, by symmetry, we had already removed AD. And we had already drawn the edge AB and AF. And our first case was to use BK. So that didn't work. So the next case is going to be to use BC instead. So case 2 would be the edge BC is used. And again, I'm just going to make a table like I did before. So I'm going to now have another round of analysis. It's kind of similar of edges that cannot be used alongside edges that must be used. This is our hypothetical Hamilton cycle, and we're just trying to force a contradiction somehow. So if I am using BC, so if I do use BC, then can somebody tell me a starting point for my either cannot be used or must be used? Tanner.
Cannot use BK.
Okay, now we cannot use BK. I like that. So we'll put BK there. All right. Now what's something else that we can say based on that? Alyssa?
You have to use,
KE and KF. I love it. Yes, absolutely. So we must use KE and KF. Let me add that to the must be used list. KE and KF. All right. Anybody else want to jump in? Sam, are you feeling a little better? CE cannot be used, right? Because otherwise we would have a premature cycle. So I like that. Let's remove CE. Cannot be used. Based on that, do we have some other edges we can talk about? Linda? CD, right? Has to be used. Okay, I like it. Let's add CD to our list. That's in the must be used category, C and D. Okay, very good. Anybody else want to try something? Sam?
What about,
EG and EH. Well, would you agree? I've already used EK. So between EG and EH, I would have to use one of those two edges. Because I'm required to use two that are incident with any vertex, but I don't know which of the two I would need. I could do subcases. Right? But I don't think we need to. I think we can argue this without getting too many more hypotheticals involved. Yeah. DG and DJ. Well, again, I don't know which one of those I'm going to use. I have to use one of them, but I don't know which one. I want something definitive, guys. Is there something? Yes, Ashley.
we cannot use FH or FJ.
Right, look at vertex F. I've already used two of the edges that are in blue there, so I can remove FH and FJ. So that's in the cannot be used pile. FH and FJ. Great. And based on that, what else can I say? DJ. I'm sorry? You must use DJ and which other one? IJ, right? Because J only has those two vertices or those two edges left. So I must use DJ and IJ. So I'll put that over here in the must be used pile. DJ, very good, guys, and IJ. Okay, so we got that. Now what can we do? Oh, we're getting close.
You must use HD and HI.
HE and HI because there's only two edges left for vertex H, so I have to use HE and HI. Those are in the must be used category. HE and HI, and as I go about this, I believe that makes another closed cycle. And this time it was vertex G that was the only one missing, right? So again, I'll write down that we get a premature cycle. And we should write down the cycle as what we've obtained. So A to B to C to D to J, then to I, and then to H, and then to E, and then to K. Go on to the next line here, and then down to F, and then back to A. Yeah. So we have missed out on just one vertex again this time. Questions on that? This one's kind of moderately involved. It's not crazy, but we did have to use symmetry. We did have to use cases. And we had to be a little bit patient with this domino effect of required choices. Kevin, you look like you're poking at the graph a little bit. Is it okay? So far, so good. Anybody have questions? Marcus?
Can you explain, I get the idea, but can you explain a little bit like the wording of standing by symmetry? What is that?
Well, what I mean by that is, if you look at this original graph, you cannot use all four of the outside edges.
Right.
So we could go through four cases and we could say, well, let's suppose we don't use AD, and then that's case one. And then case two would be, let's assume we don't use DJ. And then case three would be, let's assume we don't use AF. And case four would be, assume we don't use FJ.
Okay.
And we could do each of those. But the idea here is that if we just do one of those cases, we're going to capture basically every scenario, because if I remove this edge, it's no different than if I had removed that edge.
Yeah.
It's just it becomes like a mirror image of the graph. Or if I'd removed this edge, it's like flipped this way. So if there's no symmetry, then you would have to do all of those cases, right? Like, so you might be wondering, so some of you might be wondering, draw it again. You might be wondering, after I removed this and I forced these two edges, I did BC and BK. I did both of those cases. Could I have just done one of them and argued that it was symmetric? Could I have just done the case when BK is used and not do any of that over there? Well, I would argue that we actually do need to do both of these cases, because we are using AF, which is down here next to BK, so actually this edge was connected here too, right? So there's a big difference. If I'm using edge AF, right, there's a big difference between whether I'm going to use BK or whether I'm going to use BC, because BK has a vertex that connects to F, whereas BC has a vertex here that's not connected to either of those two. So there's no symmetry there, so I do have to write out all the cases.
So you're saying,
It's a little tricky. It's a little tricky.
you're saying like kind of assume AD is not used by the cycle, and then by symmetry do that without loss of generality.
Yeah, I mean, I think what I wrote is probably
No,
okay. So, you know, just there is symmetry here, and so let's just assume without loss of generality that we're not using AD. I think you can just probably express it that way. Yeah. So anyway, I wanted to do one that wasn't like just too trivial, because they obviously these can be kind of tricky. These can be kind of tricky. Well, ordinarily, I think I would probably try to cover this next little section. I want to talk about bipartite graphs and trees, but I think I'm going to wait till Thursday, because I'm just not really up for a lot more talking right now. I think what I'm going to do is, I've got two problems on this group work. The first one is to just decide whether the two graphs are isomorphic or not. So it's kind of practicing the same thing we did last week. And then the second one is to show that there is no Hamilton cycle, so the stuff we were just going over. So you and your group can decide whether you wanna focus on problem 1 or problem 2. You only have about 15 minutes, so it's not a huge amount of time. There we go. Pass this one out. This is group work 10, guys. Don't have a lot of them. And once you've got the handout, grab 2 or 3 people and yeah, come on up to the board and see what you can do. There we go. And I don't want anyone getting sick. I've been using the markers, so there's hand sanitizer here. Feel free to use as much of that as you want. I'll come around and give you a hand. Here, I can erase it. Put this out of your way. And let's see what you guys come up with. Yeah, sure. Yeah, well, from here, if I'm using both of these. If you're not using that one, that one's. If you have choices, Linda, then you have, that's what it's happening.
Yeah.
Then you have to say, well, one case would be I use the IJ. The other case is I use the edge, you know, IG.
The vertex is the same.
So you were like. Oh, so before we have this one? Yeah.
Recycle in the second.
Yes, yes. Only one way to kind of get your opinion. That is great. It's not one right. Good question.
Yeah, I don't think there is any recycle.
Okay.
Since I kind of missed out on last Thursday, I didn't even get to watch it. The reason we're focusing more on the Hamiltonian cycles because the Hamiltonian paths are just more trivial.
I would say that there are less obvious results. Than there are with the Hamilton cycles. It's not that they're more trivial,
Okay.
but it's often the case that you want to work on cycles anyway. If
Okay.
you are trying to visit a bunch of vertices starting from your house, chances are you ultimately want to be back at your house again. So I think in a lot of the applications, you want to have the cycles.
Okay.
Yeah.
Gotcha.
But some of the principles still apply. You can only have 2 edges, incident with a vertex used by a path. And in fact, the first and last vertex, you can only have 1 edge used.
Okay.
Because you're only departing once and then you never come back because it's a path.
Okay. Yeah. Thank you.
Do you think?
Yeah.
Do you think that there's like not so much more to learn about the Hamilton cycle as because it doesn't get as much research, or it's just something that doesn't have any.
The research that's been done is very. So we're either gonna just kind of get our feet wet with it, which is what you would normally do in a class like this.
Right.
Or you're gonna devote the entire semester to like doing the whole study of this one
Yeah.
topic. So obviously in this class, we have to choose to kind of just get our.
I'm thinking there's probably some kids like took the class when he was 12.
Yeah.
And devoted what?
And got super stoked by it. Yes.
And absolutely.
Uh-huh.
Yes.
Maybe that'll happen to somebody in here. Okay, Tanner's off to a good start on that, I think. I like that.
Yes. Number 1 is a 3 cycle.
You guys get the other one done already?
But the latter one has no 3 cycles.
Let's see what you say. Oh, I love it. That is so succinct. That is pretty good. All right. See what you can do on number 8.
We gotta say no. We can't use it properly to prove it.
All right, you found a 3 cycle in that second graph. 8 to 7 to 3 to 8, yeah. And you can just say that the first graph does not have a 3 cycle. But that doesn't need anything more than that. I can look at the graph. says valid. There's not really.
Oh, yeah, that.
It's more just an observation. Okay, number one was easy.
I had a question.
Yes.
So when you were doing like, showing all these tables, there's P. We're gonna have to do some. No, the other one, sub.
Premature.
Premature metrics.
Yeah.
Premature subcycle.
So.
Are you saying that?
No, we can't use any, we can use all premature stuff like that.
Okay.
Premature stuff.
Outer-
Yeah, cause you can always.
I was thinking. It's kind of obvious when you, by symmetry, we have exactly.
Awesome.
Okay, well,
Symmetry without log. Yeah, log.
That exhibit.
No, it's like law function and.
Oh.
The top maybe?
Yeah.
Maybe.
Don't have, like, the first one, need the.
So, I guess we should.
Yeah. But they don't have to cycle, they have to, they got all the.
A,
I think we always.
we would have to use A, B, we have.
Hey, grab A.
Okay.
The first one, the next one.
Yeah, we had to use A, B. Well, let's start with what we have to use here, I guess. We have to use
Okay, yeah.
No, it's fine. Yeah, you also have to use.
A, B,
Yeah, AD and BG.
to make this one black as well.
Right. Yeah. So far, so good.
Oh, we have to.
All
this over
here. Everything's all.
Yeah.
Which means
The other time too.
we have to use all of these. And.
Oh.
And we have.
So we're not,
We don't have to use that one.
we're not using that. We're not using that one.
We have to use those.
Wait,
We have. to-
Because look at her tech.
Oh,
We
wait.
Come on, we needed this one, this
Oh, wait, then we already, then we can't pass, we can't, there you go.
Yeah, you're forced to use, three different edges that touch B.
Yeah, we're forced to use three edges.
BA and BC and B. So yeah, that's another contradiction. So we didn't actually get a premature cycle here. We just simply ended up required to use too many edges that are incident with the same vertex.
Yeah. Okay.
It's good.
We're on either side. Once we're here.
We got this.
Start here, go.
Um,
We have to use this one.
can you explain the bisymmetry? Let's remove AC.
Yeah.
Oh, but it's.
Well, it's just kind of the,
We have to do two.
yeah, kind of the outer edge again,
Right.
the whole picture's symmetric, right?
So
So we
Um,
one of the outer edges.
What I would say is if you use both of the curved edges,
As soon as we use one.
then in addition to using these two side edges, you would have a premature
So.
big oval on the outside.
Yeah, that's what I'm thinking.
If you use both, of them,
Yeah.
that would be a contradiction.
Oh.
Therefore, I know at least one of them I cannot use. And without, and by symmetry, we can assume it's not this one. Right? But I mean, you would need to, yeah, because I would need to be convinced that, well, why is it that I can't use both of the curved edges?
Both A,
So,
B.
yeah, that would help a little bit.
And.
And that is just the street.
You guys doing okay? Yeah.
Yeah.
Yeah, no free cycle, this one doesn't have a free cycle, that's pretty easy.
Because we have some premature subcycles.
What you can do with part A there.
I was,
Anybody need some help? Okay, all right.
This is our, you can't do it. So, like, we're forced to use all these, all the ones that we erased.
We need to show the vertices.
Can you explain why are you forced to use the flat one on the top?
So, you're forced to use this, you're forced to use this, you're forced to use this.
That I believe,
Right?
yes.
And then we'll have these two down here.
Yeah.
You have to do them in hand, one of
You have to pick one, I agree.
So say you pick this one, I
can't
can
use
use
that.
this one, and it remove this one.
Oh, yes, yes.
So
Well,
then,
now you're already done, because this vertex in the lower left corner is kind of, there's no other edge that you're allowed to use to enter and leave.
Oh my gosh.
Yeah.
Yeah, I like it. For now, this is okay, obviously, ultimately, you gotta have the right.
yeah.
Well, it could be actually-
We only have our.
Oh my gosh.
For the time. Great. Anybody need some help?
Guess we can go over here.
Progress here.
I'm still trying to convince myself of the first part, AC and GI, like it makes sense what
And
you're
that's
saying.
because you are not.
The wording of that.
Yeah, that's a good point, because
You
if
usually see if you shows.
both of these for. Then you.
Not, maybe not.
He's saying that I can't use this entire thing.
If you use both.
Yeah.
You
so
could say.
We have to remove one of the pieces. of
One,
it.
I actually would say by
So you
symmetry,
just take one of them. back. So by
A,
symmetry, you either remove this one, or this
I guess
one. It doesn't matter.
not,
So we don't need to break it into cases. Because removing the bottom is gonna have the same effect.
so then you have to, you don't use AC, you have
So that's what we mean by the.
A,
by
B,
symmetry.
A to the outside. Yeah, you're getting.
Yeah, it's kind of the same logic as the one that we did. You go outside the rectangle, and it didn't really matter which piece you.
Well, you have to.
It didn't have the same effect.
Because
So you
vertex
just have to
has
remove
a
one.
reason.
If you had multiple things, it was the original subcycle, which fails. So if we use both,
It's also, we have to. That's
Yeah.
part of the,
One,
that
like,
first statement.
yeah, we are going, we're gonna have.
Have to use vertex because you have to be able to enter
Yes.
every,
Yeah.
That's one, okay.
every vertex.
Yeah, you can think of it that way as well, but I think that
I think it's fine.
makes the same.
Yeah.
It's just maybe a little bit clear if you use.
Is that right?
If they both use.
Yeah, because then you're connecting those and.
To a certain degree.
We wouldn't get to use that. Let's try it out. Well, actually, what happens, get up here, you have no information. It's nothing.
Same idea, we can't use the entire outside.
Their vertex C has only one usable edge.
Is it symmetric?
Because you've already said it, now you're realizing you also think.
So we have to remove it. So now we do one of it.
It's always about the other.
AFC was one of those.
Sometimes it's just gonna be, oh, there's so many edges that I can't use, that I don't have enough edges to make. That's what happens on the C. That are usable, right? If I go visit vertex C, I have no way to leave.
Oh, that's true.
Stranded in that vertex.
We're not
I
using
don't have a second.
Delete it. No line. Right now, we that whole black line.
Exactly.
We
Yeah.
can't use that.
Oh, yeah.
You gotta place one that served you a dream.
Now, there would be.
You gotta use,
So
Well, we have to use
Yeah,
pass.
so you take the path, C,
Oh, so then we only have two cases either, we don't use, case one is,
so you're not starting.
removing PF, and then case two is removing.
So the way to add more lines, right?
Yes, okay.
Highlight. Using these.
Okay.
So I guess we'll make those ones blue, so we see. We're adding two extra line.
Well, we chose, anybody else need a hand?
You're right, so now it's. Well, actually, we can't use one. Get rid of that bad boy, gone. We ran out, let's see. Oh, no, we are.
You can just keep going.
We have to use GF. Yeah, we have to use GF.
Yeah.
For sure. We don't even know if we have cases yet, honestly.
Yeah, so like,
Continue.
Yeah, I
You
think so.
know, when they glue.
figure out if you need it, fixes one.
We'll see if it just instantly gets stuck.
Alright, right.
So you're using AG and not AF.
We are moving AF.
Why? Oh,
Because
that's
we're
by
gonna say.
symmetry. Okay, fair enough. Okay, so you're not gonna use AF, so now you have to use AG. You're right. You've not dived into cases.
Right, yeah.
Yeah.
And we're seeing we can have.
Yeah, excellent. I like it. I like it.
Okay, let's see.
E
No, I guarantee that, 'cause that has a lot of things coming out of it.
Oh, so.
But what-
How do you get
Actually, no, we just don't know how to write it.
I don't.
We need somebody to
Okay, so you got all these.
Well,
edges
we
that
can't use
have
FB,
to use,
you have.
We can't use it. We can't use it.
And then you're just sort of saying, right,
Which means we have to use it twice a cycle.
like you can't use both of these or
Uh,
three of them, they're all connected.
But then we can't go.
So you're saying.
Eventually.
It wouldn't be in the cannot be unified, it'd be up here. By symmetry, assuming that you don't use BC. Okay, so then you would have to use. AC, right,
You go to
and
F, you know,
a.
we can't, that's like.
Yeah.
But then we basically just divide.
Going, I think.
We can't use.
Well,
PH,
actually, if you
right?
use AC,
I guess I want to be wrong, so every cycle goes.
so there's no premature cycles. I know the one.
No, we can do, never mind, we're only at E.
There's a
Never
premature
mind.
subcycle, but in this case,
You can.
what happens is you actually get forced
We can still
to use
use.
more than two edges that are each.
We just don't know, we don't know which one we're using, so we
I have to
can.
use
Can't
AD
say-
because of B, I
Can't
have
have
to
anything
use
together,
AC
right?
and AB because.
I'm trying to see if there's anything else we want to do.
I'm wondering if maybe actually. Because
I think it is.
It's like you go, well,
I'm trying to see if
But
there's.
it's nice to see that there isn't always going to be
Say we don't.
sometimes you'll just either have too many edges consistent with a vertex or a force, or another thing that can happen is.
How about you said we chose to go to
There's
that.
only one remaining edge
And then
that's feasible
how-
on a certain vertex.
But so you're gonna say that in every case,
I mean, it's hard to.
Things like that can.
We could do
It's
what I
very
said,
much
but.
a reinforced,
but you're gonna.
process, I have.
That's the side of foods you use.
A little tougher, it's highly select.
Can I use the fat side of the marker?
Can I get it?
Well, I was thinking, you know, one of the cases on that, I think. One of the cases-
Hey guys, whenever you get to a nice stopping place, you're welcome to take off, and just park outside.
I hate this darkness. Yes, did you guys?
Oh, no, but that's my point.
We hit.
If we have the case now around this, then
So,
it's easier
is
to
it
decide.
to say that we can't do each?
Oh, no, but that's what I'm saying.
Each them to have to be-
I think that's all we got time for, right? So we'll just-
Uh-huh.
Oh, I was gonna say, so the case should just be around this one, around that, we have anything.
Yeah. It's this small and long. And
No,
then
like
second.
HF, HD, and HG.
Yeah.
Don't put
And then everything else is T.
Yeah, I
I
got it.
essentially divide.
I'm gonna go watch yourself later.
You're right,
Yeah.
right, that.
I like.
Very quite precise, it's
Yeah.
actually going.
But then everything else.
Yeah. So check my solutions on that, we'll see how I can work it out, but yeah, you're right, that one I mean is a little.
I knew it was right.
Yeah.
The intuition is perfect, I probably want to demonstrate some of the.
Maybe on a quiz.
Maybe something like that, yeah, exactly. You guys feel okay back here? This one takes more time. Yeah, that's the reports, and I think, you did it for now. Probably would.
Oh, wait, we're not. Well, we're. It's like.
Always have to do that.
Oh, we have.
You're leaving something out here, something.
And then you've already had
out
two.
here, but then, yeah, putting it all together, there's gonna be.
Something that's already happened.
There. That.
At the beginning.
Oh, no,
we don't have
I
the.
think the last one we were
Oh,
gonna
yeah,
have
that's
like.
like 30s.
If we're not getting too far.
No, but we had to, and that's where it ended. And then because-
Good job, everybody.
Because of symmetry, this case.
Yes, right.
Oh, wait, there goes.